Hello everyone, and welcome to Central Physics Reviews. This is a channel that I'm starting because I've noticed how common it is for all of us learning physics to get so caught up in memorizing equations that we lose sight of the big picture and never get around to building a conceptual intuition for the physics described by all of this underlying math. So, unlike some of the other physics channels here on YouTube, I'm not going to try to teach you physics from the ground up. Instead, the episodes on this channel are going to go over some of the most important topics in physics from a bird's eye view, collecting the relevant equations and going further to explain them and add context, so that your knowledge of the formulas we use in physics can turn into a fundamental understanding of the physics itself. So whether you're preparing for an exam tomorrow or just want a better intuition for what you learned in class today, these reviews will be here for you. Today in this introductory video, I wanted to start off with a discussion of the question, what is physics in general? And the broad answer is physics is simply a science that attempts to describe things that happen in the world. And that seems like a very ambitious task, and it is. And in order to make it more doable, we need to be very specific about what exactly it is that we're trying to describe when we go ahead and do physics. And in particular, what this means is that we need to define something that we call a system, which is the thing that we want to understand, the thing that we want to describe the behavior of. And everything outside of that little box we draw that constrains and defines what we mean by our system and what we're trying to describe is going to be external to the system. And the point of boxing off our system like this is that we no longer care about the little microscopic details that go on within the system. And we also no longer care about the little microscopic details that go on within all of the parts of the world that are external to the system, or sometimes it's called the environment that the system is in. What we end up caring about is simply the interaction between the thing that we've called our system and everything else. And the system can really be whatever you want it to be, from a box sitting on a table to the entire observable universe. But you do need to specify, whenever you're trying to do physics, what the system is that you're trying to describe. Now, once we've set that down, once we know what our system is, the next step in doing physics is to figure out all of the possible states of that system. And so here we have a very simple, trivial example of a system that consists of a ball and three boxes. And there are three possible states of this system. The first of which is the ball is in the orange box, so we can call that state A. The second is the ball is in the green box, and we can go ahead and call that state B. And the third state, as you might have guessed, is the ball being in the blue box, and we can call that state C. And so we've labeled every single state that the system can possibly be in. The ball can't be outside of the cups. The ball can't be in two cups at once. This is it. It's either in state A, state B, or state C. And this seems like a trivial task. And in this case, it certainly was, but it's also a very important one. Because if you want to describe what your system does, you first need to describe what your system can do. And that's what outlining all of these different possible states is all about. Now, there are some systems, like the one we're going to look at here, which is a particle on an infinite line, where you simply can't label every single individual state that the system can be in. The particle can be in the middle of the line where I've drawn it here, or it can be significantly to the right in this state over here, or it can be to the left in this state over here, or anywhere in between. And because the line is infinite, there are infinite possibilities for the state that this particle can be in. And so we can't write them out. What we need to do is we need to be a little bit more clever. And what physicists do is we invent variables that can take on infinitely many values and specify what the state of this system is. So in this case, the answer is quite simple. All we need is a variable to tell you what the particle's position is. Usually we call that variable x. And that variable can take on any real number from minus infinity to infinity. So if the particle is where it's drawn right now, maybe we can say that x takes on the value of -2. And if the particle is closer to the middle of this line I've drawn, maybe we can call that x equals 0. And so on. So if the particle is to the right of this line, we can give it a value x equals 2. And it goes on to infinity to the right and to infinity to the left. And no matter where the particle is, there's always a value of x that captures the state of the system. So here, instead of putting a separate label on every independent state of the system, we have a single variable that can take on any value to tell us which state the system is in, basically to tell us which position the particle is in. Now, there are more complicated systems where even a variable isn't enough. If you imagine a particle in a plane instead of a particle on a line, and you draw the same position variable x on the horizontal axis, knowing what x is no longer tells you the complete state of the system, because the particle can be over here and have some value of x, maybe that's x equals 5, or it can be down here and have the same value of x equals 5, but be in a different state. So now knowing what x is simply isn't enough information. And in fact, what you need is a second variable, which we can call y, to label the vertical axis. And now with these two pieces of information, you can fully specify what the state of a system is. So for example, if the particle is all the way in this upper right corner, the state of the system might be, say, x equals 10 and y equals 10. And if the particle is maybe in the upper left, you have x equals minus 10 and y equals 10. And I know this is very basic stuff, but the whole point of this is to emphasize that in order to label or to specify the state of a system, you now need to specify two things. You need to tell me what x is, and you need to tell me what y is at the same time. Now, one really interesting thing about physics is that you don't have to use specific variables to specify what the state of a system is. You could choose to use the variables r and theta like in polar coordinates. So if we draw a line from the origin to the particle, we can give it some distance from the origin r. And we can draw an angle to the x-axis over here, and we can call that theta. And now you don't have to tell me what x and y are. You can instead tell me what r and theta are. And I will still know equally well what the state of a system is. It will be uniquely determined. So another way to do this is to specify r and theta. So that's a beauty of physics, because physics doesn't tell you what variables you need to invent to describe the system. All it really tells you is how many variables you need, right? Notice here that you need two variables if you're using xy coordinates, and you still need two variables if you're using r theta coordinates. And that's because there simply isn't a single variable that can specify the state of the system. And what we say in physics is that this system has 2 degrees of freedom. And that means the particle can move in 2 independent directions. So whatever variables you end up using to describe the state of your system, you're going to need 2 of them because the particle can do 2 independent things. Well, once this is all said and done, once we have outlined all of the different possible states of our system, here it's, for example, all sets of combinations of x and y, we still haven't really said how the system behaves or what happens in the system. We've only outlined what state the system can possibly be in. In order to figure out what happens in the system or what state the system will be in when you look at it, we need some sort of rules that tell us what happens in the system. So let's start with the really simple system that we had before, where we just have 3 cups and a ball. And there are only 3 states, remember, state A, state B, and state C. Now this is going to be purely hypothetical, but let's say that the rules of this system are that every time you look at it, the ball is going to be in the cup to the left of where it started. Or if it's in the orange cup, it'll go back to the blue cup. Let's say those are just the rules. So if you look at it once and you see that it's in state C, you already know, if you know those rules, that the next time you look at it, it'll be in state B, it'll be in the green cup. And the next time you look at it, it'll be in state A, it'll be in the orange cup. And so by knowing those rules, you can now predict which of these states the system will be in when you actually perform a measurement, or when you look at it, in other words. If we look at a less trivial example where we have a particle on a line, we can have a different set of rules. Let's say in this system, the rule is simply that the particle keeps moving to the right at a constant rate over time. So in this system, it doesn't care whether you're looking at it at all. The only thing the particle knows is what time it is. So let's say the particle starts over here at x equals minus 2 at some initial time. Let's call that time 0. And let's say the rules of the system say that every second the particle goes to the right by 2 units on this line. So at t equals 1, the rules tell you that whether you're looking at it or not, the particle will be over here at x equals 0. And at t equals 2, the particle will be to the right at x equals 2. And so again, by knowing the rules of the system, you can actually predict, as long as you know when you're going to measure the system, where the particle will be or what state the system will be in when you perform that measurement, when you look at the system. Now, rules don't always have to be nice. Let's look at another example here. And let's work in x and y coordinates just to keep it simple. So let's erase some of that. Let's say the rules of this system are every second, the particle is in a new randomly chosen position. So between some initial time and 1 second later, the particle might be where it is right now. But as soon as your clock hits 1 second, the particle changes position. It's all of a sudden over here. And that new position is chosen randomly. We just get a random value of x and a random value of y every single second that updates where the particle is. Now, those rules aren't particularly nice, and they seem quite strange, but still, in principle, it's something that can happen. And it'll let you make predictions, and it'll let you analyze the system if you want to know what it'll look like when you measure it. In particular, you'll know that it's quite random. So you might be asking, enough with these hypothetical rules. What are the rules in the real world? What are the real rules of physics, and how do we find them? How do we know what they are? The answer is that these rules in the real world are simply what we call the laws of physics, or sometimes they go by the name of principles. And how do we find out what these laws and principles of physics are? Well, the answer is actually quite straightforward. Physics is an experimental science. We do experiments, we perform observations, and we look at patterns in nature. And all of these observations and experiments let us find the patterns that we then call the laws of physics. Now, I'll grant you that if you just go out looking for patterns in nature and you collect a whole bunch of data about everything from, atoms to galaxies and stars, it'll be quite hard to just look at all that data and find what the laws of physics are. You'll kind of be stuck. You won't know where to start. And that's part of what makes physics hard. But there is one thing that makes physics a little bit easier than just going out, looking at data, and trying to find patterns, which is the notion of theories in physics. And what a theory really is it's an underlying explanation that tries to tell you why the laws of physics that you already know about are the way they are. So in other words, if you have a law of physics or a principle in physics, you can use that to invent a theory, which is again some sort of underlying explanation as to why things work the way you've already seen them to. And what this theory can do is it can inspire new observations and new experiments that in turn lead physicists to discover new laws of physics. So let me give you an example to make this a little bit more concrete. We've known about the law of falling objects since the time of Galileo. This is the statement that whether you have a massive object or a light object, a big object or a small object, it'll fall down toward the Earth, it'll accelerate at the same exact rate. Now, when Einstein was thinking about the law of falling objects in the early 1900s, he developed a theory called the general theory of relativity, which uses the curvature of space itself to try to explain why it is that we observe objects falling at the same exact acceleration. And in doing so, in constructing this underlying framework, the theory was able to make predictions about totally different things. For example, the theory predicted that even light, which has no mass, can still be accelerated by the curvature of space and can still bend around massive objects like stars and galaxies. And those hypotheses were then tested by new observations and new experiments. And in fact, they were found to be correct. And they led to the development of new laws of physics that told us exactly how light bent around these massive objects. So, in this way, the laws of physics that we already know can serve to inspire entirely new laws of physics, which makes this whole endeavor of finding out the rules of the real world just a little bit easier. Now, what makes physics really doable as a science is the fact that all of these laws of physics are very highly generalizable. And what that means in practice is that the same laws of physics can apply to many, many similar systems. If you look at the classical world, the macroscopic world that you and I are familiar with on a day to day basis, all you really need are Newton's law of gravity, Maxwell's equations, which tell you about electric and magnetic phenomena, and the laws of thermodynamics. And if you know those rules, you're basically set to predict how everything you can see with your naked eye is going to behave. Now, if you want to analyze a system that's moving particularly fast relative to the speed of light, then you're going to need some new rules, which come in the form of special relativity. If you're looking at a system that's particularly small, you're going to need some new rules, which come in the form of quantum mechanics. But the important thing is that you don't need new rules for every single new system you define. Any system that's sufficiently similar to another system will basically obey the same exact laws. Now, that's not to say that once you know the laws of physics, you're done. In fact, applying the rules once you already know them is another challenge in and of itself. Because as systems get more and more interesting and more complicated, the actual mathematics involved and the computations and calculations you have to do to use the rules you know to predict what's going to happen when you measure a system, that process gets increasingly more difficult. And in fact, that's where a lot of physics research is at today. It's at trying to find new mathematical techniques that help use the rules we know about to predict what's going to happen when we measure a system. So if we want to summarize everything we've just said in 3 easy steps of doing physics, I really shouldn't say easy. They're simple, but they're not easy. The first step is simply to define your system that you want to describe the behavior of. So define the system, and you also have to remember to define the possible states of the system. And its states. And once you know the states that the system can possibly be in, the next step is to go ahead and look for the rules or the patterns that tell you how the system evolves from one state to the next, if it does at all. So this involves learning its rules, the rules of the system, its rules. And of course, that's just observation and experiment. And then the last step, once you know all the rules of the system, all of the physical laws and principles, the final step is to use them to make predictions about how the system will behave. Make predictions. And usually what we're after is predicting what the state of a system will be at some future time when you want to make a measurement of it. But of course, if you're interested in different things, you can use these laws of physics to make predictions about what the system was in the past or something like that. And usually what these predictions involve is just a lot of math. So the mathematics goes into extrapolating the rules that you've learned to tell you how the system will evolve into the future, or perhaps into the past, if that's what you're after. Now, in the coming episodes, we're going to dive into a lot more detail about the specific laws that govern different kinds of systems and the math that you need to predict their behavior. So if that's something you're interested in, if you want to follow along and continue to build your intuition about what physics is and how it works, then I really hope to see you there.